So we're going to look at 7.3 and starting to look at our unit circle. We've looked at all of the pieces we're going to put together today, and that makes it kind of a good time to talk about something that often happens when you're studying early trigonometry, is that you start learning all of these concepts that seem kind of separate, and none of them really seem to connect to each other for a while, and it makes things a little bit difficult. But keep at it, keep reinforcing it, keep practicing, keep doing the exercises, and those concepts will start to come together and kind of click together. Sometimes that takes a couple days, sometimes it takes a couple weeks, sometimes it takes quite a few weeks. But eventually they'll start to talk to each other and start to work together, and you'll start to flow through problems a lot better. But that takes time, it takes practice, and it takes attentive practice. So make sure you're getting that time in. All right, as I said, we are going to put a lot of our tools together today. And last time we talked a fair amount about our more general definition of our trigonometric functions. We talked about having our sine function, instead of being just defined by opposite over hypotenuse in a right triangle, we started to define it as y over r for the y value of the intersection of the ray on a circle in ratio to the radius of that circle. And we're going to go one further today. But just to remind you, in those definitions, we had the cosine as x over r, the tangent as y over x, and the cosecant, secant, and tangent as their reciprocals, respectively. Really, all we're going to do today is take those definitions, which are general definitions for the trigonometric functions on a circle, and specify them down to a particular circle. This particular circle, which we generally refer to as the unit circle, is called the unit circle because it has a radius equal to 1 unit. Now, why 1 unit? Because it could be 1 foot, it could be 1 inch, it could be 1 meter, it could be 1 mile, it could be 1 whatever. But as long as that circle has a radius of 1 unit, then these definitions will work. And that might seem overly specific, but if you imagine, any particular angle and you're having to work with it, well, we could always, no matter how long these things have to be, we could always make a circle around it that's radius 1, and then it has an intersection point, and then these definitions will apply. So it does work in very general circumstances, if and when we need it to. So this will end up being a very, very big tool for us, a tool you're going to want to have around. You might have noticed at some point you've got this nice, fairly complicated looking diagram, and this is a fully filled out version of a unit circle, and essentially what we're going to build and talk about how to use today. So the first thing you want to get good at is figuring out or listing out or understanding where these radian measures are coming from. And we've gone through this construction at least once in these videos, but I do want to do it again, and I do want to reinforce that this is something you should be practicing doing. You should be able to go through this count and build these radian measures just, if somebody gave you a piece of paper with a circle and an axis on it, like I have here, you should be able to fill this out. If you can't yet, that's fine, but practice. Get yourself some paper, put on some circles, and, between watching videos, fill one out. When you're waiting for the water to boil for your tea or soup, fill it out. Just, if you can do it 10, 15 times and just get used to doing it, you'll start to be able to think in radians a lot more. So, without further ado, get back to our black there. So we will be thinking in terms of standard position. So we're going to imagine we start here at 0 radians. And when we introduced radians, the first big calculation we did was figuring out that a full rotation all the way around was 2 pi radians. And we're going to use that for the basis of our counting. So if all the way around is 2 pi radians, then halfway around would be 1 pi radians, or 3.1415 radians. If halfway around is pi radians, then half of that would be pi over 2 radians, and half of that would be pi over 4 radians. And that's, again, this is 3.14, this is 2 pi is 6.28 radians-ish. Pi over 2 is about 1.57 radians. So be careful of the temptation of thinking of that pi like a unit, like you're thinking, 3 feet or half an inch, half pi. It really is the number 3.1415926535892 divided by 2. So 1.57-ish is that exact value of radians at the positive y-axis. So careful about that temptation. And we're going to use these pi over 4s and count our way around this circle to fill out all of the other multiples of pi over 4. This is what I mean. So going from 0 to here is 1 pi over 4. So if that's 1 pi over 4, that would be 2 pi over 4. And notice that 2 pi over 4 would reduce down to pi over 2. So that is just a different way of looking at pi over 2. So that's 1 pi over 4, 2 pi over 4s, and that's 3 pi over 4 radians. Then 4 pi over 4, which again would reduce. Good. 5 pi over 4 radians. 6 pi over 4, which would reduce to 3 pi over 2. Then 7 pi over 4 radians. And then up here, 8 pi over 4, which would of course reduce to pi over 2. Sorry, not pi over 2. Would reduce to 2 pi. So it is nice to have kind of these axial points that we know about, the 2 pi, the 1 pi, the pi over 2, to make sure, hey, when we reduce, do we get what we're supposed to? Are we where we're supposed to be in our count? But learning to count around in terms of pi over 4 can be really handy to start thinking about pi over 4 radians and in radians in general. Now, I'm going to erase these ones that reduced because we don't need them. But it's always good to remember that they're there. Now, as we've talked about before, we could go with half of pi over 4 is pi over 8, but as you learn to calculate, pi over 8 in terms of degrees is 22.5 degrees. And 22.5 degrees, while a fine angle, isn't especially helpful. It didn't fit any of those nice special triangles that we built. Those will come in handy later. So instead of going from pi over 4 to pi over 8, I want to go back to this pi over 2 and cut it into a third, which should be about there, roughly. So a third of pi over 2, a third of a half, is a sixth. So that's going to be my pi over 6. And then we're going to do the same thing. We're going to count our way around. That's 1 pi over 6. So that's 2 pi over 6, which I'm going to leave it there and reduce it once we're done. So 1 pi over 6, 2 pi over 6. This would be 3 pi over 6, which again would reduce. 4 pi over 6. 5 pi over 6. And 6 pi over 6. Again, 6 pi over 6 would reduce to pi. So we're in the right place. So 1 pi over 6, 2 pi over 6, 3 pi over 6, technically there. 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6 would be down here. Then 8 pi over 6. And then 9 pi over 6. 9 pi over 6, which would reduce to our 3 pi over 2. Good. Ten pi over 6. And 11 pi over 6. Ending in 12 pi over 6. That would, of course, reduce to 2 pi. So it's the same kind of thing as our pi over 4s. We're doing with pi over 6s instead, and counting our way around. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6, 7, 8, 9, 10, 11, and 12 pi over 6. Do keep in mind that, 1/3 of our right angle, 1/3, then 2/3, then 3/3. We're not counting on that pi over 4, so it does go pi over 6, 2 pi over 6, 3 pi over 6. At some point, we are going to want to reduce these. So I'll reduce these to pi over 3. Reduce that to 2 pi over 3. But I think it's handy in the counting phase to count them in pi over 6s and then reduce them. This will reduce down here to 4 pi over 3. And down here to 5 pi over 3. You could count in pi over 3s if you want. The thing you have to be careful of is thirds don't match up with halves. So that is 1 pi over 3, 2 pi over 3, 3 pi over 3s. You don't stop at the positive y-axis or correspondingly the negative y-axis. So it is 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, and 6 pi over 3. So you can count the pi over 3s separately if you want to. But counting the pi over 6s gives you the pi over 3s, so we might as well. So doing this often enough does give us, or help give us, a nice sense of the radian measures. It also makes it handy to find coterminals. So if you're trying to work with an angle that's, say, 17 pi over 6, and you're like, where is 17 pi over 6? Like, what quadrant is that even in? Well, we could just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 pi over 6. So 17 pi over 6 is coterminal to 5 pi over 6. We could make that a little easier on ourselves by thinking, okay, pi over 6, a full rotation in pi over 6s is going to be 12 pi over 6. So one rotation's 12 pi over 6. So 12, 13, 14, 15, 16, 17 to count a little bit faster. Also, negatives. Say we had something like, I don't know, negative 7 pi over 4. Same idea, we're counting in pi over 4s this time. So, but we're doing it in the negative direction, but we're just counting 4 of them. There's 1, 2, 3, 4, 5, 6, 7. So 7 pi over 4 is coterminal to 1 pi over 4. So you can get faster and faster and more intuitive at doing that by getting that practice in by drawing this diagram out. Some people like to have the angle measures on this as well. If you look at this particular unit circle, it's got the angle measures on the inside. If you want to make yourself a nice fancy one of these at some point, which I highly recommend you do, and you want to put the angle measures on it, go for it. But we are going to make a little bit more of a mess of this diagram. And the reason we're going to do that is because we'd really like to know the coordinates of all of these points. Because as you recall, our trigonometric definitions, we can base those trigonometric definitions around the xy coordinates and the radius of this circle. But since this circle now has a fixed radius of 1, you may notice if that radius is 1, y over 1 is just the y value. X over 1, if that radius is 1, means it's just the x value. And that's how we get these kind of simplified definitions for the trigonometric functions. If the radius is going to be 1, we don't have to worry about, some length over the radius. If we know the coordinates of this specific point at pi over 6, if we knew its x and y coordinates, then the sine of pi over 6 would just be that y value. The cosine of pi over 6 would just be that x value. Heck, we could even write very truthfully that the coordinates of this point are the cosine of pi over 6 for the x and the sine of pi over 6 for the y. That is, completely accurately, the coordinates of that point on the unit circle. So, okay, that's all nice and good, but, how are we going to find out what those points are? Not even just these points in quadrant 1, but all of the points of intersections of our nice standard angles with this unit circle. How are we going to calculate all of these points? Well, as I mentioned, today we're mostly bringing stuff together that we've already done. So hopefully it's not too much of a surprise that we already know how to do this. We've already figured out what the coordinates of that point is. And that's the point of this exercise sheet you have down there. And I do recommend doing this. Print out this page, cut out these triangles, and go through this construction with the physical triangles. It'll help convince you of what we're going to do here. But I'm going to get that a little bit out of my way for a second. The last thing for us to remember is that we built those couple of special triangles the other day. The isosceles right triangle with the angles 45, 45, 90 in degrees, or pi over 4, pi over 4, pi over 2 in radians. And you remember I argued with your notes and even your text a little bit. I didn't want to make this length 2 or a. I wanted to say, hey, let's make that length 1 and then calculate these sides. And you might remember we got the square root of 2 over 2 and the square root of 2 over 2. And the fact that those were fractions was a little bit messy, but you'll see today why I wanted that length of 1, if you haven't picked it out already. The other triangle we built was the 30, 60, 90 right triangle in degrees, or in radians, pi over 6, pi over 3, pi over 2 triangle. And again, instead of making this side 1, I wanted that hypotenuse to be 1. Okay, it made this length 1/2 when we built the reflection of the triangle, and this length the square root of 2 over 3. Sorry, the square root of 3 over 2. So that made us have more fractions. But the reason I wanted those hypotenuse to be 1 is because if you notice, this triangle I have over here, this big triangle we have over here, actually should fit, if I drew it exactly to scale, right there. That's the same triangle. Let me draw that in over here. This triangle right here is the same triangle as this one. The radius here is 1, the hypotenuse here is 1. So that means this length down here along the horizontal is the square root of 2 over 3, and that's our x coordinate, square root of 3 over 2. Sorry, I keep saying square root of 2 over 3. That x coordinate is the square root of 3 over 2. And again, that length is 1. This is a pi over 6 radian angle. So this height here is 1/2. That's our y coordinate. So we already figured that length out when we figured out those special triangles. And now if anybody asks you what the sine of pi over 6 is, well, sine we associate with the y value, so the sine of pi over 6 is 1/2. Cosine of pi over 6, square root of 3 over 2. Tangent of pi over 6, well, y over x, 1/2 divided by square root of 3 over 2, and then simplify that. Even if you wanted to know what the cosecant of that angle is, well, it's the reciprocal of the sine, so it's 1 over the y value. So 1 over 1/2 would be 2. Secant, just take the reciprocal of the cosine, the reciprocal of the x value, 2 over the square root of 3, and then rationalize it. Cotangent, reciprocal of tangent, x over y, so it would be the square root of 3 over 2 over 1/2. Clean up that fraction, it's a square root of 3. So great, that's one coordinate. Well, okay, we've got a lot of coordinates to go, but that's one of them down. Let's go on to that pi over 4. I'd like to have its x and y coordinates. And you might have guessed, we're going to do the same thing. This triangle here, if we drop that down and go over from there, that triangle there is this pi over 4 triangle. This triangle here is this triangle here. Again, that's why I want that hypotenuse length to be 1, because that matches this radius of 1. That makes the distance here, the x coordinate, the square root of 2 over 2, and the y coordinate, the square root of 2 over 2. So what's the sine of pi over 4? Square root of 2 over 2. What's the cosine of pi over 4? Square root of 2 over 2. What's tangent of pi over 4? Well, square root of 2 over 2 over the square root of 2 over 2. It's 1. Very nice. Well, we still got a lot of points to go, so I do kind of want to speed up here a little bit at some point. How are we going to handle pi over 3? Well, I could give you a little while to think about that. But ideally, you'd see that this triangle is the same as this triangle. It's just flipped now so that the pi over 3 is down there, the pi over 6 is up there. Still has a hypotenuse of 1 because that radial length is still 1. So that short length is still 1/2. The long length is still the square root of 3 over 2. It's about 0.8-ish, so 0.5 and 0.8-ish and 1. So it really has the same lengths as the pi over 6. They're just in the other orientation. The x value is 1/2, it's the short length, and the y value is the square root of 3 over 2. So that didn't even really take any more work. It's just a triangle in a different orientation. And that's what you're asked to do with this exercise, is cut out these triangles, write in their lengths in ratio with those hypotenuse of 1, and fit them in those spaces and see that those triangles fit exactly in those locations and give you those coordinates, just what we're doing here. And I want you to actually do that, because the hepatic or kinesthetic, the physical act of drawing that out, cutting it out, putting it in place and labeling everything is really going to lock a lot of things in your mind. Now up here at pi over 2, okay, we're not going to be fitting a nice triangle in there at pi over 2, but we don't have to, because we know those coordinates. It's a circle of radius 1, so that y value is 1, x value of 0, that's the point 0, 1. Just like down here, that's the point 1, 0, because the x value, the radius is 1, y value is 0. So again, the sine of pi over 2, if some mean person came up to you and said, hey, what's the sine of pi over 2? Well, sine of pi over 2, the sine's the y value, so the sine of pi over 2 is 1. Cosine of pi over 2, 0, the x value. Tangent of pi over 2, well, tangent's supposed to be y over x, so the y over x, 1 over 0. Can we divide by 0? No, we can't. So it's undefined. And that's okay. You can't take the tangent of pi over 2. Secant of pi over 2 be 1 over the x value, so 1 over 0. The secant of pi over 2 is also undefined. Sine and cosine are nice. Sine and cosine you never get undefined, but the others you get undefined every once in a while when you try to get those division by 0 errors in there. So we have to be a little careful, but still, just knowing those coordinates, we can answer any of those questions for sine, cosine, tangent, cosecant, secant, cotangent, anything we want. Okay, so that's actually, we've broken out this whole quadrant here. 3 more quadrants to go. But hopefully, it'll seem pretty reasonable. Whoops. Whatever that was, it wasn't reasonable. Hopefully it'll seem pretty reasonable that this triangle here is also going to fit over here. And that this point is the same height as this one. They both have the same y value, square root of 3 over 2. And they kind of have the same x value, except x values in that quadrant are negative. It's going to be true for 3 pi over 4. 3 pi over 4 is at the same basic location as pi over 4, just that the x values are negative. So it's those same numbers, just with the positives and negatives changed. Similarly, the 5 pi over 6 and the pi over 6, that's in a symmetric location. So it's the same triangles, just considering those lengths that are going in our negative direction for the x are considered negative lengths. Again, negative lengths will bug us for a while, some of us anyway, but negative length, it's a real thing, it just means backwards. So don't let the fact that we're considering some of those lengths to be negative to throw you off too much. This value at pi, well, we know it's negative 1, 0, the coordinates of that point, because the radius of the circle is still 1. Okay, so that was just kind of copying those points over. What about down here? What about at 7 pi over 6? Well, it's got to kind of be the same as this, doesn't it? It has the same x value as that does. So it's still going to be negative the square root of 3 over 2. And it's as far up as this is down. So it's still 1/2. It's just negative 1/2. All of the rest of this are the same values we have on the ones above, just the positives and negatives have changed. This 5 pi over 4, it's the same basic location as the other pi over 4s. It's just both the x and the y's are negative. 4 pi over 3, it's got to be the same as the 7 pi over 6, just flipped, because the horizontal leg has become our vertical leg, and the vertical leg has become our horizontal leg in our triangle. So negative 1/2, negative square root of 3 over 2. Down here, of course, the 0, negative 1. 5 pi over 3 is going to be the same as 4 pi over 3, just with now a positive x value. Seven pi over 4, same as all the other pi over 4s, except with a positive x value and a negative y value, because we're in quadrant 4. 11 pi over 6, same as 1 pi over 6, frankly, except that it has a negative y value. And you might remember a video or so ago we talked about the sine value and the cosine value in quadrant 1 were all positive, because those x values and y values are positive. The sine value down in quadrant 4 has to be negative, because the y values down there are negative. So it's the same logic that we've had before, just kind of condensed down into this nice tool. And again, this nice tool is this same tool that we had before. The only difference here is it's got the angle measures on it in degrees as well as in radians, and if you want that on your diagram, great. But these coordinates, notice they have that same pattern. It's all 1/2 and square root of 3 over 2s. Build this unit circle. And all we have to know to build this, even in our heads once we get comfortable enough with it, is we have to know how to count our standard radian measures around, and we have to know these two circles. So these two circles are our friends. because they allow us to make this big unit circle idea, which is a big friend. I know, I'm a nerd. What are you gonna do? Oops. I can't get rid of it. That's fun. Okay. So, I've said this before, I'll say it again. Do this construction, do this drawing, draw yourself this thing, do it a handful of times, make a super nice one, put a little bit of calligraphy in it if you can, have it laminated, carry it around with you. This tool is going to be your buddy. Because one of the things it's going to allow us to do is answer all kinds of questions like these really quickly, and once we're used to it, fairly easily. So if we want to know what the sine of 5 pi over 4 is, well, our unit circle has a 5 pi over 4 on it. Where's our 5 pi over 4? It's down here. What color do I want? Our 5 pi over 4 is down here. So if we want the sine of 5 pi over 4, we remember sine is our y values. Our pi over 4s go with the square root of 2 over 2s and square root of 2 over 2s. So the sine of that 5 pi over 4, it's in quadrant 3, so it better be negative. Square root of 2 over 2. And that's it. Tangent of negative 2 pi over 3. That sounds scary. It's negative, it's a tangent. But all we got to do is find where that is on our circle. So again, we're going to count our pi over 3s. So that's our 0. Negative 1 pi over 3 would be here. Negative 2 pi over 3 would be here. So that 4 pi over 3 is coterminal to our negative 2 pi over 3. So essentially, we don't usually write this, but it's not trivial that that's the same as the tangent of 4 pi over 3. I want to give ourselves a little more space here. Ideally, you guys have this paper with you so you can see what's on it. So all we need are the coordinates and to remember what our relationship is for tangent. Since the tangent is our y over our x, the y is negative square root of 3 over 2 over negative 1/2. Do be careful about your positives and negatives. So the negatives are going to cancel out. I'm going to multiply both sides by, or top and bottom by 2 here. Give us the square root of 3 over 1, or just the square root of 3. So that's the entire answer. Cosine of pi over 2, well, cosine's the x values. At pi over 2, our x value is a 0, so 0. Cotangent, secant, and cosecant are always a little tougher because they're the weirder ratios. But just remember that this is 1 over our tangent, so find your tangent and flip it. Secant is 1 over your cosine, so find your cosine and flip it. Cosecant, 1 over sine, so find your sine and flip it, make its reciprocal. So cotangent 7 pi over 6, negative 7 pi over 6. First we have to find that, and again that's our counting in the negative direction, counting pi over 6's. 1, 2, 3, 4, 5, 6, 7. So that's coterminal to 5 pi over 6. And I could write that that's equal to the cotangent of 5 pi over 6, but I don't have to. I just know we're at this location, and whether that's 5 pi over 6 or negative 7 pi over 6, it's going to have the same points associated with it because that intersection is going to be at the same location. So what's our cotangent? Well, our cotangent is reciprocal of our tangent, so it's our x's over our y's. So negative the square root of 3 over 2 over 1/2. Again, those halves are going to undo each other. You could do this a different way if you wanted to. And we'd end up with negative the square root of 3. Great. Secant. Notice the first thing I'm kind of doing is trying to figure out what quadrant we're in, like where is this thing? So 3 pi over 4, well 3 pi over 4 should be over here in quadrant 2. And secant, well secant's like cosine. Cosine in quadrant 2 is negative because the x's are negative, so we expect a negative answer here. Our secant is the reciprocal of our cosine, so it's 1 over our x, 1 over our cosine value. And what's our cosine value of 3 pi over 4? Well, it's negative square root of 2 over 2, negative square root of 2 over 2, technically over 1, or under 1. So its reciprocal is going to be negative 2 over the square root of 2, and you rationalize that into negative 2 square root of 2 over 2, or negative the square root of 2. Or you might remember that we built this from 1 over the square root of 2, so you can just flip that over. However you want to think through that's fine. Cosecant of pi. Cosecant is 1 over our y value, because again it's the reciprocal of sine. So at pi, we got to figure out what our y value is, so we go over to pi. At pi, our y value is 0. So this is going to be trying to be 1 over 0, but since we can't, don't do that with your zeros. The theta. 1 over 0, but we can't do that, so undefined. So having this tool will allow us to evaluate our standard angles very nicely and very quickly. And we want to take advantage of that. Big square hit. Okay. Now, see, I want to bring this back up here because I don't want to go away from my circle. I want my circle. Kind of a big circle, but that's okay. Better than a small one. Okay. So we're told, given an angle alpha, oops, given an angle alpha such that where the sine of alpha is negative 1/2 and the cosine of alpha is negative square root of 3 over 2, determine the values of the remaining trigonometric functions. So we got 4 more. So the big thing is, where is this going to happen? Well, if sine and cosine are both negative, that means the x values and the y values are both negative. So that's only happening down here in quadrant 4. So if we wanted to find out what the angle was, we could kind of back figure out the angle. So the y value of negative 1/2 and an x value of the square root of 3 over 2. So this is happening here at 7 pi over 6. But we don't actually need to know that to be able to proceed in this problem, because we know that the tangent of this angle is y over x. Well, that means it's the sine value over the cosine value. And we've had this quotient identity before. So negative 1/2 over negative the square root of 3 over 2, which will simplify into 1 over the square root of 3, which will rationalize into the square root of 3 over 3. We know that the cosecant is the reciprocal of sine. So I could say it's 1 over y, but it's really 1 over the sine value. So 1 over negative 1/2, or just negative 2. Multiply by 2 top and bottom, or multiply by negative 2 over 1, however you want to go about that. Let's see, if we want the cotangent of alpha, it's just the reciprocal of tangent. We could take the reciprocal here, but taking the reciprocal there would be easier because it's just the square root of 3 over 1, or just the square root of 3. And last but not least, our secant, 1 over our cosine value. Oops, that should be an alpha. 1 over the cosine of our angle. And why am I writing 1 over cosine instead of 1 over x like I did before? It's the same thing, because remember, the x value is the cosine value. The cosine value is the x value of intersections on the unit circle. So either way, since this problem is expressed in terms of sine and cosine, I'm writing it in terms of sine and cosine. But if we wanted to use the x and y values, it's the same process. It's just you could write it differently or not. So that's 1 over negative square root of 3 over 2. And I'll write it out the other way. You could, write it out as multiplying by the reciprocal if you wanted to. Don't forget that negative when you do. So it would be negative 2 over the square root of 3, which you'd rationalize into negative 2 square root of 3 over 3. So, similar process to what we were doing before. If we want to simplify down here, like this is just an algebraic simplification, but it is based on these kinds of relationships. We know, for example, that the secant is 1 over the cosine, and we know tangent is the sine over the cosine. We can essentially write all of the trigonometric functions in terms of sine and cosine anytime we want. So we could multiply top and bottom of that by cosine, or if you prefer working with your fractions this way, that's fine. Dividing fractions, same as multiplying by reciprocals, whichever way you're comfortable with. So that's 1 over the sine of theta. And just, 1 over sine of theta is fine, but also remember that that's cosecant. Sorry, phi. Theta. No, theta. That's cosecant theta. So secant theta divided by tangent theta simplifies into cosecant theta. And this kind of manipulation, this kind of almost algebraic manipulation of our trigonometric functions will allow us to do a lot of somewhat surprising simplifications at times, making complicated expressions with lots of trig functions in them, and they'll kind of collapse on each other to often make very, comparatively small and tight expressions, just by using these variations of what our trig functions mean. I got more down here somewhere, right? I got a bunch more down here. Let me move them up here. Just because I want my circle. I'm going to move away from my circle. I guess we didn't need the circle for those last couple, but we really need these relationships. Okay. What did I do? Just overwhelmed my graphics card. That's what I did. Alright, I gotta let my computer calm down a little bit. Doesn't like changing that all that much that fast. Okay, let's look real quick down here. Reference angles. Reference angles are a nice tool. They often kind of give people a little bit of trouble. I think a lot they get confused with coterminal a fair amount, and people try to make them a little bit more complicated than they have to be. Oh, that's terrible. That's okay. So it's our positive x-axis and our y-axis. So what a reference angle is, I'm just going to grab 5 pi over 6 for the fun of it. 5 pi over 6, it's a little high for 5 pi over 6, doesn't matter, but just for the sake of argument. So if that's a 5 pi over 6 radian angle, you remember our circular definition really dealt with kind of putting that triangle down here and thinking about where that triangle fits in there to come up with what the coordinates were for that point on a circle of radius 1. So when we're looking at this triangle, I'm going to say this little orange triangle here, notice it doesn't have a 5 pi over 6 radian angle in it. 5 pi over 6 is about 150 degrees. There's not a 150 degree angle in this triangle. There is, though, this little 30 degree angle, this little pi over 6 angle. And when we're talking about a reference angle, that's the angle we're talking about. The little angle that's inside the kind of triangle we are imagining in our other quadrants. Now, of course, this can't actually be a triangle because it's got a negative x value there. Okay, it's got a positive y value and some r value. So it's not an actual triangle there, but we're visualizing as if there's a triangle there. And that is handy because we knew the coordinates of the point over here in quadrant 1 and just kind of moved them over to this location. Remember, all we had to do was change the x value from positive to negative. And that's the idea of these, is that the sine of 5 pi over 6 should be not necessarily exactly equal, but highly related to the sine of its reference angle, the sine of pi over 6. The only difference is it might have changed from positive to negative or from negative to positive. So as long as we know what quadrant we're in, hey, this is in quadrant 2, and hey, sine is positive in quadrant 2 because y values are positive in quadrant 2. So it's going to be the same as the sine of pi over 6, but make sure it's positive. Sine of pi over 6 we know is 1/2. Check your circle if you need to. And since we're going to want it to stay positive, well, just leave it alone. That means the sine of 5 pi over 6 is still just 1/2. It's the same value as its reference angle and even has the same sign. Now, if somebody asked us what the cosine of 5 pi over 6 was instead, well, the cosine, it should be the same as the cosine of pi over 6, because The reference angle for 5 pi over 6 is 1 pi over 6, but it might be positive and it might be negative. And we only know whether it's positive or negative depending on what quadrant the original angle was in. Since this original angle is in quadrant 2, and we know cosine's negative in quadrant 2, we know we have to grab the negative answer. So if we check our circle, the cosine of pi over 6 is the square root of 3 over 2, and we make sure we give it the negative value. Now we'll do a couple more examples, but one of the important things about reference angles, make sure we're always measuring our reference angle in a positive orientation, because we do want it to be a positive angle, and towards the x-axis, not the y-axis. So it's not this angle to the y-axis, it's the angle to the x-axis. Now why is that? Why do we always measure to the x-axis and never to the y-axis? Well, because that's how our sine and cosine are defined. They're defined on the assumption that we're measuring to the x-axis, like we do in standard position, not to the y-axis. So if you measure to the y-axis, you get the same basic values, but all your sines and cosines would be switched. All your x's and y's would be switched. So always make sure you're measuring your reference angles to the x-axis, either positive or negative. I mean, the x-axis in the positive orientation. Either the positive x-axis, if we're over here in quadrants 1 and 4, or to the negative side of the x-axis if we're in quadrants 2 and 3. So that's the only thing to be really careful of, is to make sure we're always measuring to that x-axis, not the y-axis. So the cosine of 3 pi over 2, well, it might first be handy to remind us where 3 pi over 2 is. 3 pi over 2 is down here, so we're looking at this angle. And what's our reference angle? Well, technically we could measure it in either one, but I'd probably measure this one. That reference angle is a positive pi over 2. So this should be the same as the cosine of pi over 2. We just have to be careful and make sure we have the right sign, the right positive or negative. Now the interesting thing with this one is that it's 0 either way, because you remember, our point up here at pi over 2, ugly, up here at pi over 2 was the point 0, 1, so our x value is 0, so it doesn't have a polarity. It's not positive nor negative, so it's just 0 either way. Now you might be thinking, well, why didn't we just grab from the unit circle the 0 down there? We could have. Why didn't we just grab the points on our circle for the 5 pi over 6? We could have. But essentially what reference angles do, because we're always measuring the short angle to the x-axis, to or from the x-axis, we're essentially turning any angle we're ever dealing with into a quadrant 1 argument. So this cosecant at 3 pi over 4, it's like, I don't want to deal with 3 pi over 4. Can't we just deal with 1 pi over 4? Well, we can, because 3 pi over 4 is over here in quadrant 2. 3 pi over 4. It has a reference angle of 1 pi over 4. So it should be the same value as the 3 pi over 4, just maybe it's positive or maybe it's negative. Is it going to be positive or negative? Well, cosecant has the same plus or minus as sine. And since in quadrant 2 the sine is positive, this thing is going to be positive at both pi over 4 and at 3 pi over 4, where our y values are positive in those two quadrants, our y values are negative in those two quadrants. So whether it was at pi over 4 or at 3 pi over 4, both of them have the same y value. So we've turned a quadrant 2 argument into a quadrant 1 argument. All we had to do was be careful about whether it's positive or negative. Keep in mind up here, when we were in quadrant 2 with cosine, that had to change to a negative. But for here, it doesn't have to. Check your circle. The y value at pi over 4 is the square root of 2 over 2, so 1 over the square root of 2 over 2, which will simplify into the square root of 2 once you simplify it and rationalize it. So reference angles really just allow us to make quadrant 1 arguments out of everything that we might want to. This is often handy when you're working with tables, or if you want your arguments to match so you can kind of multiply things together. Like if you had, say, the sine of, we use the 5 pi over 6, and somebody wanted to multiply that by the sine of 1 pi over 6, well, you can't really multiply those together in that form, except that the sine of 5 pi over 6 is the same as the sine of 1 pi over 6. It even has the same positive nature. So we could just rewrite this as the sine of pi over 6 times the sine of another pi over 6. So we can turn into the sine squared of pi over 6 because we can express it as its reference. If we did that same thing with cosine, we could still do it. And I'm going to stick with the 5 pi over 6. And the cosine of pi over 6, the only difference is when we change to the cosine of 1 pi over 6, it's going to be the negative version of it, because 5 pi over 6 is in quadrant 2 and cosine's negative in quadrant 2, times the other cosine of pi over 6. So we can still now bring those together. It's now just negative cosine squared pi over 6. Fair? You might remember I said at the beginning there's a lot of details that you're learning that have to kind of all click together to make a lot of this work. And that's kind of what I'm talking about here. Being aware of, what quadrant am I in? What sign does that mean I'm in? Calculating reference angles, thinking in radians. You've got to kind of be doing all of those things at the same time to make these questions work. And that takes some time. Takes some practice. And kind of just, I guess, be okay with that. Let it take that time, let it take that practice, and try not to get overly frustrated with it. Just do these exercises, and it'll come. Oh, that's just what I was saying there. The reference angle, theta prime, some people use that notation, it's fine notation. Always positive, it's always acute. Formed between the angle and the x-axis. That's what I said before, the reference angle and the quadrant of the lies. That's to evaluate any trigonometric function for any given angle. Yeah, that's what I said. So the big thing is, if we're in quadrant 1, no matter how many, whether this rotated negatively to get here, whether it rotated around positively 8 times and stopped there, anything that stops coterminal there, the reference angle will be that positively oriented measure. If you're in quadrant 2, it will be that positively oriented measure. If your terminal side is in quadrant 3, it'll be that one. If your terminal side's in quadrant 4, it'll be that one. Notice positively oriented, measured from the terminal side acutely and the x-axis. So notice all of these will always have to be acute angles. The only exception is if it was at it's straight up or straight down. Like, for example, at 3 pi over 2, you get a right angle, which isn't acute. But other than that, there'll be acute angles. You just have to remember what quadrant it came from so you can make it positive or negative as appropriate. Oops. I didn't want that. So determine those reference angles. What's my time doing? Ooh, a little over an hour. So determine the reference angle. Just draw it out. 7 pi over 4. Well, that's 1 pi over 4, 2, 3, 4, 5, 6, 7 pi over 4 is down there. So 7 pi over 4 has to be down there, which means this little reference angle, 1 pi over 4. And that's it. Negative 11 pi over 6. Well, we know 12 pi over 6 is a full rotation, so 12 pi over 6 backwards would be there. 1 less. Negative 11 pi over 6. Or, again, count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 5 over 6s. You'll get quick with that as you practice. So what's that angle going to be? Well, that's the other pi over 6. So that's its reference angle. And do draw it out. A lot of people try to do these things in their heads. Don't do this stuff in your heads. Makes your heads hurt. Ooh. That was fun. I don't know why that. Oh, that was page 5. Okay. Am I missing any pages here? Graphics card's not happy today. So, find the exact value of each expression. Okay, so this is kind of going to be combining. We're almost done here. This is going to be kind of combining a couple things. We do want to be able to visualize what's happening in these problems. Some of that visualization will come with time. For right now, draw it out. If you have a problem like this, grab your unit circle or draw one out, or both, preferably both. Negative 5 pi over 4, well, negative direction, and 1, 2, 3, 4, 5 pi over 4s is going to be right there. So we could go to our unit circle and grab that value if we wanted to. Or we could recognize, hey, our reference angle would then be 1 pi over 4. So this is the same as the tangent of pi over 4. But recognizing that tangent in this quadrant writing upward for some reason. Tangent in quadrant 2 is negative. It would be the negative of the tangent of pi over 4. And if it helps, remember tangent is y over x, so we have positive y values and negative x values in this quadrant, so Positive divided by a negative is going to be a negative. So the negative of the tangent of pi over 4. Check your circles out. Tangent of pi over 4, or check your charts out. Tangent of pi over 4 is 1. So it's just going to be negative 1. And you could have done that from the from the square root of 2 over 2 over the negative square root of 2 over 2. Or you could have done it from the reference angle. Either way. Go down to 2 here. 7 pi over 3. Now, 7 pi over 3, we kind of have to do a little bit more work. Not a lot. Do notice that, this is more than a full rotation. We know it's more than a full rotation because it's, 7 pi over 3 is larger than 2 pi. We know it's larger than 2 pi because it's larger than 6 pi over 3 if we got common denominators there. So it's going to be a full rotation and then some. So in pi over 3 is a full rotation 6 pi over 3, so it's 7 pi over 3. So 1, 2, 3, 4, 5, 6 pi over 3, 7 pi over 3. Oop, decide to make a circle. 7 pi over 3. But that 7 pi over 3 is coterminal to the cosine of 1 pi over 3. And coterminal, we don't even have to worry about reference angles. Because, yeah, this thing's reference angle is pi over 3, but it's also coterminal to pi over 3, so it's got to have the same positive negativeness because they're in the same quadrant. But either way, cosine's positive in quadrant 1, so all we need are those coordinates from our unit circle, and those coordinates from our unit circle, the x value on our unit circle, would be 1f. Okay, I want to do these things, the last couple a little bit faster because I want to get you guys out of here. Secant of 3 pi, well, we know halfway around 1 pi, all the way around 2 pi, so 3 pi is going to be another halfway around. So all the way around and then back to there. And from our unit circle definition, I could have put that dot anywhere I wanted. I'm particularly going to choose to put that dot where this radius is 1. Because we can. That makes the coordinates of that point -1, 0. Secant is the reciprocal of our cosine. So that's going to be 1 over the cosine of 3 pi. So 1 over cosine is our x value, so our x value on the unit circle. And the x value is -1, so 1 over -1, -1. Skipped cotangent for no particular reason. Negative pi over 2, so negative pi over 2 is down there, coterminal to 3 pi over 2. So this is going to be the same as the cotangent of 3 pi over 2. So those have to be equal because they're coterminal. But if we wanted to use a reference angle, the reference angle would be the cotangent of just pi over 2, and we'd have to make sure we get the right sign, the right positive or negative. So we don't know which one until we did it. But because I don't want to deal with any of that, so I'm just going to use the unit circle. So all we have to do is know that point. That point which is on the ray for 3 pi over 2. It's also on the ray for negative pi over 2 because they're coterminal. And we know that point is 0, negative 1. We know cotangent is the reciprocal of tangent, so x over y. So 0 over negative 1, which is 0. Okay, last example. Given that the cosine of alpha is 2/3, and we're in quadrant 4, that says quadrant 4, find the exact value of the remaining 5 trigonometric functions of alpha. We've done problems like this before, and we'll do problems like this again. So quadrant 4 means we're down here somewhere. I don't know what that angle is, and I'm not worried about it. It's not to scale as long as we're in the right quadrant. And we have a choice here. We can either think of this as a x value and an r value, which would give us a 2 and a 3. And then we'd have to calculate this other side. Or we can think of this whole thing as an x value, 2/3, and the hypotenuse as a 1, and calculate that other side. Again, since all we're looking for is ratios, it doesn't matter which one of those we do because the ratios are going to be the same. It's just is it scaled in or scaled out? Is it zoomed in or is it zoomed out? So really, do whichever one is easier. I think the 2 and the 3 are easier, but if you like the 1 and the 2/3, because who doesn't like squaring a 1? You just get a 1. Either way is perfectly fine. I'm going to do it that way just because, I don't know, why not? I feel like it. Because we're doing unit circle today. So that's going to be our 2/3 squared plus our y squared has got to equal our 1 squared. Always make sure you let that hypotenuse be 1, or the hypotenuse be what it's equal to. So then 4/9 plus y squared equals 1. So y squared equals 1, which I'm going to turn into 9/9 because we're going to need common denominators, minus 4/9. So y squared is equal to 5/9, which means y is equal to plus or minus the square root of 5/9, or y is equal to plus or minus the square root of 5 over 3. Notice it still has the over 3 like we would have had if that was a hypotenuse. But no matter, all we have to do is make sure we know whether we're grabbing the negative or the positive, and because we're in quadrant 4, that y value is negative. So we have an x value here of 2/3 and a y value of the square root of 5 over 3. Gosh, my computer's being weird today. So, from just having those, well, that's the cosine value, we were given it. That's the sine value. Put the y over the x to get the tangent, take the reciprocal of that to get the cotangent. You can find all of the rest of those. I'm going to end this before my computer panics too much. One thing I want you to make sure with these notes, I don't want these note videos to take the place of you doing your research. So make sure that you're going through your text, going through those videos, trying to play with these notes, trying to play with the section, and not just watching this note video and thinking, okay, that's probably plenty. That can leave some gaps and leave you with some trouble. I'm going to try to fill in as many of those gaps, but this is, 1 to 1.5, sometimes 2 hours a week, as opposed to, say, 4 to 5 hours of lecture a week. So try not to let this take the place of that research on your own. That's why I try to hold them off a bit, so you kind of have to do some of that research. Ideally, this is clarifying some information, making sure your notes are correct, all of that kind of stuff. So keep up with that. Let us know if you need anything or have any trouble with some stuff, and have a beautiful day.